Cool. Okay, so scientific notation lets us be accurate with our numbers, and also is more convenient because writing out a number like 14 trillion light years or 14 billion light years is a very long number, very hard to write out. If you had to write that out on your homework assignments over and over again, they would take a lot longer. So what we do instead is we break this into a decimal portion and a exponential portion. So our decimal part be a number that is between 1 and 10. So that in this case, this example should really be, I'll leave that there. But if we were to convert this 14 billion, we'd say 1.4, that's our decimal portion. And then the exponential portion is indicating how many zeros come between the actual decimal place and that decimal place. So for 14 trillion, we would actually just count these. So the implied decimal places here. We'd say it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 decimal places. So you'd have 1.4 times 10 raised to the positive 10. In this example here, we have an example of a small number. So if a positive exponent moves our decimal place to the left, negative exponent moves the decimal place to the right. Or I guess reverse, depending on how you're thinking about it. So if you see a negative exponent, very small number, positive exponent, very large number. The way that it's moving this decimal place is by raising 10 to exponential powers. So when you raise something to an exponent, you're multiplying it by itself that many number of times. So 1 raised to the first power, which would be 10 multiplied by 10 one time. So it's just 10. Actually, let me write this out here too. So there's a reason there's a 1x in front of these. So 1 times 10 raised to the 2 would be 10 times another 10. So you do 10 times 10, you get 100. If we do it 3 times, right, 10 times 10 times 10 is 1,000. So every time you're doing that, you're indicating that you're multiplying by another 10. When you have this negative exponent, it means that you're not multiplying by 10, but you're dividing by 10. So this 10 raised to the negative 1 is 1 divided by 10. 10 raised to the negative 2 is 1 divided by 10 times 10. So there's 2 10s in the denominator on the bottom of that equation. And if you're not familiar with calculators, calculators will abbreviate this with an E. So for example, 1 times 10 to the 3 will be 1. Sometimes it's a capital E, sometimes it's a lowercase e. But this would be 1E3. And so what that E means is E is just times 10 raised to whatever number comes after it. So you can have 1 times 10 to the 3, 1E3, or you can have 1E negative 3. So if you type it into your calculator, this is the easiest way to do it. And your calculator will give you answers like this if they're too big. So we want to take any number and express it in scientific notation. Like I showed you before, you move that decimal place. So you move the decimal place to obtain a number between 1 and 10. And then you write the result multiplied by 10 raised to the number of decimal places that you move the decimal point. So if it's a big number, you'll have a positive exponent, small number, negative exponent. So 5,983 can be rewritten in scientific notation as 5. So right, we move the decimal place, so we got a number between 1 and 10. 5.983 times 10 to the 3. Yeah.
Is there any time when there's 2 digits in front of the decimal, or is it always a 1 digit?
It can be, okay, for the purposes of this class, just do 1. Okay. If you are trying to compare 2 very large numbers, you might have 2 numbers in front of the decimal place just for easier comparison, but that's more of a style choice, but it would not be incorrect. Yeah. So if we have a small number, then we're moving this decimal place to the right, 1, 2, 3, 4 spots to get a number, right, 3.4 between 1 and 10. And then we say times 10 raised to the negative 4. You cannot leave off the times 10 to the whatever exponent because that would completely change your number. Right, 3.4 is very different than 0.00034. One is a very small number, one's a, I guess, average number. Depends on what you're talking about. All right, so back in 2016, the US national debt was $18,416 billion. Much easier to write that, but maybe less impactful to write that in scientific notation. I'm just going to write this a little larger. 2, 3. So if you do have the convenience of commas there, you don't have to count every single one of the zeros, right? We can skip those because they're in groups of 3. So you'd say that this is moving at 3 places, 6 places, 9 places, 12 places. And so we'll end up moving it over 13 decimal places. Because then our number will be 1.8416 times 10 raised to the 13th power. Cool. Everybody tracking? Any questions? All right, we'll keep going. So again, for small numbers, we do something similar, but we're moving the decimal in the opposite direction. So we want a number between 1 and 10. So we're going to move this over 1, 2, 3, 4, 5 spaces to get, all right, the 5 there, 3.8 times 10. And because we have a small number, we move that decimal place to the right. We're going to have times 10 to the negative 5. Unfortunately, we don't have a way of denoting like groups of 3 digits for very, very, very small numbers. So just be very careful counting those zeros. If you have something where you can mark the page, definitely mark those as you go along because you can get lost in your count. Okay, so part of the reason we have scientific notation is so that we can keep significant figures for very large numbers specifically. For a lot of things, we count them with discrete numbers. So like the 7 pennies here, right? There's no wiggle room for that. There's exactly 7 pennies there. You could take 1 penny away and you'd have 6. You could add another penny, you'd have 8. But if you were to weigh yourself, well, if you were to weigh this gold bar on a scale, it's going to give you some number, but that's not going to be the exact precise mass of that gold bar. The same way you step on a scale, it says, like yesterday when I stepped on the scale, it was like 239.2. But what it's doing is it's rounding up or down that next digit, and we don't know what it is. So for discrete things like the number of pennies, we could say that is exactly 7. For something like weight or length, there's going to be an amount of estimation there. And we use significant figures to keep track of how much we've been estimating. So for one example, scientists have concluded, actually this is probably from 2016 or so, but that the average global temperature had raised by 0.7 degrees C since 1880 when they started tracking it. And that 0.7 degrees C is reported like that because that's as far as they can be sure of, because that's sort of the collective estimation is past that number, we can't say, you know, is it 0.76, is it 0.75? There's not enough confidence to say that. So you can't report something with more zeros than that. We'll talk about how to keep track of that in terms of calculations. If you took all of these numbers, though, that they had from all the weather stations around the world for all of these different years, if you type them in, your calculator or your computer would give you a long string of numbers because your calculator doesn't know how precise any of those measurements are. It'll just give you everything. So in a way, if you reported all of this, or if the scientists reported all of this, they would be lying they would be misrepresenting their measurements. So scientific or significant figures is a standard way of reporting this sort of uncertainty. We'll do some examples. Right, so scientific numbers are reported so that every digit is certain except the last. And that's because usually we're going to measure as far as we can be certain. And then it's on something like a ruler, which we'll see in a second. If it's in between tick marks, you can estimate where it is in between there. But if we keep this sort of standard, then every other scientist who reads your measurement afterwards will know that that last digit was estimated, and they'll know the precision of your instruments that you used. So, like I said, here's our example. We have this ruler, and we have a quarter, and we're trying to measure the diameter of the quarter. You could imagine that we used like sheets of paper or panes of glass or something to get these exact lines. But through the beauty of modern science, we can zoom way in on this. We can see that this quarter comes all the way up to 20. And even though these tick marks aren't marked in between, we can figure it out because 20, 30, halfway in between is going to be 25. So then we know that each of these tick marks is 21, 22, 23, 24. So the level that we can be certain up to is 24. So we would say that this is 24 point, and then this is where our estimation comes into play, right? So how much farther past 24 is this? 5, 6, both good guesses? Yeah, so, right, based on who's looking at it, based on even which side of this line we're looking at, because I don't remember if it goes, it's kind of even hard to say, like, is that on the outside of the line of the quarter? Is it on the inside of the line of the quarter? But based on who's looking at it, that's going to be estimated. But if we keep track of this and we say, I'm going to go with 6, 24.6 would be our measurement. Anybody else looking at this would say 24 was certain, they estimated the 0.6, which is what's on the slide. So for any of these things, we're going to measure up to the last line, and then whatever goes past that little bit is where you're making your guesswork. You know, solid guesswork, measured guesswork. So for this balance, if we're measuring out this blue substance, which reminds me of Breaking Bad, we've got markings that are every 1 gram. So again, we can zoom in on this, and we can see that, yeah, right? So we go, this is 1 gram. So we're going to be at 1 point, we'll estimate that next digit. 0.1, 0.2, 0.3, it's kind of hard because that line is so thick. Where is it in that line? But that's where the guesswork comes into play. So we'll go 1.2. And then we always want to mark down what our units are as well. So 1.2 grams. So for a lot of these things, especially for balances and stuff, it's pretty straightforward how to do this. You just have to make sure, because we'll have some glassware in class that actually counts down from the top. So just make sure you know where 0 is and which way the tick marks are going. So for this one, again, I've got 1 gram and 0.1 gram increments. So if we look at our scale here, change the color. This is 1 gram. Every one of these little ones is 0.1. So we're at 1.2. So 1.2. And then again, estimating where that is after that. So 1.26, 1.27. So the precision and the number of digits or decimal places that you'll have in your reported measurements will be based on the instrument that you're using. And it's always estimating 1 digit past the smallest marking. I do also want to, I always forget to put this example in here. We're measuring volumes of liquids, the graduated cylinder, which I think we'll be doing next week. You'll get tick marks like this. So we'll say this is 10, 5. So say we got something like this. That's 10, 20, say that these are milliliters. When you pour a liquid into a beaker like, or into a graduated cylinder like this, especially for the smaller ones, you get what's called capillary action. Ooh, lots of crazy zooming. So if I draw in our water like this, it'll form this almost like contact lens shape. And so when you measure this, you're measuring from the bottom of that shape, because the amount of liquid that's actually making up this little bit on the edges is actually a very tiny amount. And so we're not going to take that into account. So something like this would be 10. So our measure would be 10.123, 10.35 milliliters. Sorry, nope, I read that wrong. Please feel free to call me out when I do that. 13.5. There we go. 13.5 milliliters. And then, well, we'll get to that in lab. There are some that have 0.2 markings, and those are weird. Okay, so those are that. Again, just another example here. So if we have a thermometer, we're measuring the temperature in the hot tub. If we have this reading on our thermometer, so we've got 100, and this is actually 110 up here. So 105, again, we're just measuring 100. 101, 102, 103. 0.5, 0.4. Yeah, I think there's usually like a range of like, right, maybe 0.3. There's usually like a range of 3 digits. You can kind of get in there and just, again, make your best guess. Like 103.4. And any of those would be acceptable answers, as long as you're close to that mark. All right, so for counting significant figures, well, I guess go back here for a second. So if we had this 103.4, those are all significant figures. So everything that you record or estimate off of an instrument is significant. So you'll carry those onwards. But sometimes you'll be given numbers in a calculation, and you need to figure out which of those digits are significant. And especially when it comes to zeros, that's where all the confusion happens. And actually, as an example, I do want to say that if we had, for instance, a ruler, or measuring something, more often than you might think, we'll get something that measures exactly on the line. So if this is, let's just call these centimeters. So let's say this is 5 centimeters, and we've got 0.1 markings. So it'd be 5.00 centimeters. And you need to include both of those zeros, because otherwise, if you put 5, if we're assuming the last digit is estimated, now we assume that 5 is estimated. So you lose all the precision of your measurement. But by including these 2 zeros with it, or let's say we had another thing that went out to, whoops, do another color here. So we had another box that we're measuring, and it comes out to exactly 5.1. Then we say this red box is 5.10 centimeters. So if you look at it and it's right on the line and you estimate that as being 0, you need to include that 0 when you report that number, because now we know that that 0 was your estimated number and everything else was precise. Yeah.
So when the examples it said 0.7 and it said not to add the zeros onto that.
If it's 0. Oh, you mean the first example? Oh, yeah. So that one was like, that was their final reported number. You can't just add zeros onto that, because you can't add zeros there because they had calculated with a bunch of different numbers. And we'll talk about how to carry through significant figures through calculations. But that's different than reading something off of a ruler or something. Does that make sense?
So if it was a final product,
you wouldn't just add extra zeros on.
it's only when we're estimating things.
When we're estimating things, you'll add zeros. We'll talk about significant zeros right now, because sometimes you will have zeros like that in your final answer. these are the three major rules. We got a couple other rules that cover some other cases, but they fit into these three. So for all non-zero digits, those are significant. All non-zero digits. So for these numbers here, we say that 1, 5, actually, I'm going to do it like this. So according to rule number 1, which we'll do in orange here, yeah, it looks orange. The 1 and the 5 are significant. And then our second number, both of these 1s are significant. We haven't talked about anything about zeros yet, but any number that's not 0 is significant. So interior zeros are also significant. So that's a 0 that's between two non-zero numbers. So we look back at these first two examples. We have this 1, 0 for 1.05 that falls between two non-zero numbers. So that's also a significant digit. And we can go back on these examples on number 2. These ones we would highlight green because they're significant. Our non-zero numbers are significant. And then for this other example, right, non-zero numbers, interior zeros, so between two non-zero numbers. This is and then this next rule is the one that's where we start to get into things that are generally more tricky. So I would recommend making like a 3x5 card, write these 3 rules on it, and just have that out when you're doing homework. Because every time you come across a number, you can go back and reference those rules real quick. I think it was this class where I was mentioning on Tuesday, there's a lot of things that will not be intuitive until you learn them and get a feel for them. This is one of them. You have to work on and develop the skill of identifying which numbers are significant. All right, so trailing zeros. Good. Some colors up there look terrible. Trailing zeros, or zeros to the right of a non-zero number coming after, are significant if there is a written decimal point. Pretty big if. So for 5.01, sorry, 5.10, because we have a decimal point, that 0 is significant. Then we go back and do our other rules. These are non-zero numbers, so they're also significant. For this last one, do the orange first because I got the highlighter out. So 5 is going to be significant. And then again, we have a decimal place. That means that all the zeros that are trailing or come to the right of a non-zero number, those are going to be significant. And then we go back up to this example actually at the top, because there's a trailing 0 there. So that would be significant. So when we go through, we can count these. You have a question?
So the ones to the left are not.
The ones to the left, the zeros to the left are never significant. If it comes before a non-zero number, it is never significant. So we can go through and we count these sig figs. All right, so for this first one, it's going to have 3 sig figs. And I will abbreviate very quickly sig figs as SF. This one also has 3 sig figs. This next one has 5 sig figs, 3 sig figs. And really for these, it's all the ones that I highlighted, right? So 5 sig figs. Sorry. Thank you. 4 sig figs if I can count. Okay, so those are the 3 major rules. You have 2 more rules. One of these is one that I will write. I'm just going to tell you now. I will write this as not a trick question, but it's a question that everybody misses. It's not, no. It's a question that a few people miss every time. And so I really want to highlight this point because I try to highlight this point a lot, is that if we have trailing zeros before an implied decimal point, right? So there's no decimal point written on either of these. Those are ambiguous. We cannot tell which of those zeros are significant or not. So if you get questions like this, and I say, how many sig figs does that have? There's no decimal place, it's just implied. They're going to be ambiguous. Because we use zeros in two ways. Oh, go ahead.
Can you just say the sentence again? Because I'm copying what you're saying.
Okay, yes. If we have trailing zeros before a decimal place and implied decimal place, those are ambiguous if there's not an actual decimal place. And I know I didn't post Tuesday's lecture. Please remind me, I just forget. But those will be posted and I can upload the transcript too. So these are ambiguous. There's no explicitly written decimal place. So we don't know which of these are significant because we use zeros in two ways, right? We use zeros to say that there's nothing there, that value is zero. We also use it to indicate which place our non-zero numbers are in. Because we wanted to write 1,000, you need to use 3 zeros, excluding scientific notation, which is why scientific notation is important, which is this example here. So like 350 might have 2 or 3 significant figures, depending on how this zero was intended. But if we write it in scientific notation, we can avoid that confusion. So 3.5 times 10 to the second will have 2 sig figs, but 3.50 times 10 to the second has 3 sig figs. And you'll notice that this follows our rules from the previous slide, where we have a decimal place and we have trailing zeros. So all 3 of these are significant, which is one of the beautiful things, or one of the very convenient reasons that we use significant or scientific notation is because there's almost always a decimal place when we do that. So if there's a decimal place, then we know that every number that's written down in this decimal portion is significant. So when a number is expressed in scientific notation, all trailing zeros are significant because we will have a decimal place.
I'm confused about which one of those two is correct.
It depends. So it depends on, there are 2 different ways of expressing the correct number of significant figures. So if we had measured this as 350, and we only had a ruler that measured to the tens place, then we'd want to use this because we'd only have 2 sig figs there. We could only go to the tens place. Right. Yeah. So again, and then I said this previously, but leading zeros are not significant ever. So these zeros here work the same way that our trailing zeros up here do, but because there's this decimal place, we know that they're not adding anything to the number. They're just putting it far enough back so that we know that this is in the 10,000th place. And same for this one. All right, so they're just locating the decimal place. If you can remember these 3 rules, they apply to everything. So we talked a little bit about exact numbers before, or discrete numbers, I guess. If we're counting a number of pennies, counting a number of pencils, or counting a number of people, those are all exact numbers, and they have an unlimited number of significant figures. Because we know that, so say for the pennies example, that's 7 point, right, goes on to infinity. We know that there are exactly 7 pennies. When I step on the scale, I don't know if I'm 239.2 or if I'm 239.22 pounds. That number is going to stretch out to infinity, but I can't know what it is. unless I get an accurate enough scale. Actually going to cross this one out because for the purposes of this class, we're just going to treat conversion factors as exact. So you don't need to worry about which conversion factors are defined quantities. If you take Chem 1, that's something that you'll have to cover there. And by then, it'll be a lot easier to memorize that along with everything else. Okay, so a little practice here. Remember, for A, how many significant figures do we have? 4, right? All non-zero numbers, easy. Just count how many there are. That's how many sig figs. For B, I'm going to cross this one out. How many sig figs is that? 3. Leading zeros. So these are leading zeros because they're in front of our first non-zero number. Never significant. But we do have a decimal place. So this 0 is significant. So that is 3. Let me write these in here. 3 sig figs, 4 sig figs. For C, 2 sig figs. And so we only keep track of sig figs in the decimal portion of our scientific notation. The rest of it doesn't change any of the sig figs. Cross this one out because this is an exact conversion, right? So these units are defined sort of based on each other, that a centimeter is 1/100th of a meter. So I guess to give you other examples of what exact conversions, it would be like a foot is 12 inches, like a pound is 16 ounces. Those are exact because they're defined that way. What about E? 3. Yeah. Again, this is a leading zero, so not significant. But because we have a decimal place and trailing zeros, those are significant. What about F? Ambiguous.
It's like if we're on a test, the answer would be, if it was a multiple choice, it would say ambiguous.
Yeah, one of the choices would be ambiguous. So on this one, I can give you an example of what I would write. A would be 2 sig figs. B would be 4 sig figs. C might be, throw something random out, 3 sig figs. And D would be ambiguous.
You always forget the other U.
I forgot the other U, yeah. Ambiguous. Cool. I think that's, oh yeah, we got to do calculations next. Okay, so that's how you determine if you're getting a measurement or if you have been given a number from the book, that's how you'll determine sig figs. When we do calculations with our sig figs, we have sort of standard methods for determining how to carry those through. So when we do a calculation, you can end up, right, if you took 2 divided by 3, we would get 0.66 repeating. How many of those do we keep? This is the method of how we determine which ones we keep. Or this is what we're going to talk about. So for simple one-step ones, cover that. And then for calculations that involve multiple steps, you only round your final answer. So if this was, let's just say that this is 2.3 plus 5, we would only round at the very end. So we would do 2 divided by 3. That would give us 0.66 repeating. You can keep that number in your calculator with all of that precision. And then you would do plus 5. And then your final answer, you would end up rounding based on the rules that we're going to talk about right now. But make sure on every step, you keep as many digits as possible. And I can show you if you don't know how to use the answer key on your calculator. It's a very easy way to do it instead of writing them all down on a piece of paper, then typing them back into your calculator. All right, so these rules are fairly simple. We have multiplication and division. This is why you need to be able to count the number of significant figures. The result of multiplication and division carries the same number of significant figures as the factor with the fewest significant figures. Right, so if you have two measurements and you multiply them together, your final sig figs is determined by your least precise measurement. So you're not inflating how well you know that number. So we took this first one and we did 5.02. How many sig figs does that have? 3 sig figs. And for this next number, 89.665, 5 sig figs. And this last one, 2 sig figs. So typing that all into your calculator, though, like I was mentioning before, you'll get this long number, which if those were all significant, would be like 7 sig figs. But clearly, our smallest is 2 sig figs. So what we're going to do is we're going to start from the leftmost number. It's always going to be a non-zero number. So in this case, we start with the 4. That's our first significant figure that we're going to keep. And we move to the right one. That's our second significant figure that we're going to keep. So we're going to keep the 4 and the 5. And then we either round up or round down based on the 0 or based on the next digit. So in this case, it's 0. So we leave it as 45. And that'll be our final answer. Does that make sense? Yeah.
So if it was 45 point, let's say like 1/6, then you would have made it 45.1.
No, so if it had been 45, so
Sorry, 0.2.
if it had been 45.2, this still would have been 45.
Okay, so
If this had been,
so you round to what's right after the decimal point, after the 2 significant figures, but as long as it's not over 5, then you would keep it.
mhm,
So if that next digit, if the 0 would have ended up being a 6 or a 7, then it would have been 46.
yeah, so if it had been 45.5 or greater, then we would have rounded this up to 46. But you see that final number still has just 2 sig figs. Okay, so for this next one, we have 4 sig figs here. We have 3 sig figs here. Again, decimal place, trailing 0. Those are significant. So our final answer then is going to have the fewest number that we did our calculations with, so 3. So we're going to keep the 9. Again, I'm starting with that leftmost non-zero number. 1, 2, 3. We're going to keep those 3, but we're going to round based on this 9. So this would be 0.966. Round that up. So that's the correct number of sig figs there. Any other questions there? Okay.
When you move left, you were going to add a 0 at the end.
Oh, how I added a 0 in front here?
Yeah.
Oh, okay. Yeah. So this is a good question. You don't have to put that 0 there. For me, it's easy to lose that decimal place sometimes. And then if you go to write that number later, if you write 966 instead of 0.966.
So would it be okay if I would put 0.966 and not add a 0?
It would be, yeah.
Yeah. Okay.
Yeah. Right. So leading zeros are never significant. So this doesn't change anything except making sure I know it's a decimal place. So rounding, which we did cover just now, but I find the wording of this a little bit confusing. Use only the first or leftmost digit being dropped to decide in which direction to round. So if we were to say, let's go back to this actually. So we have this one, we have the 965. The first or leftmost digit being dropped is the 9. And so we're dropping the 9 and everything after it. But because this is 5 or more, we round up. If it was 4 or less, like we did on another example, we round down. So for example, if we had a number that was 2.33 and we were keeping 2 sig figs, we would round that down and just have 2.3. If we had 2.37 and we were just, again, 2 sig figs, then we round it up to 2.4. Okay, so again, we got, oh, I have to calculate these ones actually. So we have 3 sig figs for this first one, 3 sig figs for the second one, 4 sig figs for this one. How many does this last one have? 1. Oh, sorry, not the last one. I guess there's one more. This next one is 1 sig fig. Yeah. The last one, 2 sig figs. So let's type this straight in, 1.1. You don't actually have to put the 0 into your calculator because it doesn't actually change the number, but 1.10 times 0.512 times 1.301 times 0.005 divided by 3.4. So even though we're doing a combination of multiplication and division, the rules are the same for both. So we just keep our smallest number of sig figs. But I'm going to write out this, most of this number, maybe not most, but more than is necessary. Okay, so if we had, based on our sig figs over here, just 1 as our fewest, then we find that leftmost number that's a non-zero number. So in this case, our 1. And then our answer will be rounded based on the number after that, which is 0. So it'll be 0.001. So you notice too that I typed all of those numbers into my calculator. And even though it's doing all of those individual steps, we don't round at any of those steps, just with our final answer. All right, so in this next one, without me writing it out, which is our fewest number of sig figs? Yeah, 3 sig figs. Because this one is 6, 4 sig figs. So we can do 4, calculator, please. 4.562 times 3.9987. Throw the 0 in there. All right, so this gives us this number. We're not rounding. Divided by 89.5. So we'll get 0.203822. Our smallest number of sig figs is 3, like we identified before. So we're going to start with the 2. It'll be 203. And yeah, it'll be 204, because the next digit after that is an 8. Cool. Addition and subtraction changes things up a little bit. And here we're using the smallest number of decimal places. So when you're doing this, it can be easier to write it old school style with a stack and lining up those decimals. Because then you'll get, right, so our final, or our answer here before rounding would be 5. 4 plus 2 is 6, so it's 11. 1624, 9.414. And so the rules for dropping is now decimal places. So 5.74 has 2 decimal places, and these other ones have 3. So we're only going to keep 2 decimal places in our final answer, which would be 9.41. You're adding and subtracting, you're not counting the number of sig figs.
Yep, 214 in the book, but
Oh, did I do the math wrong? Double check. Did somebody else do the math? Did I do it right? On a calculator?
it's in the books, but I don't know.
Wait,
I think we messed up on the part right after the decimal.
that makes sense.
Yeah, my calculator got 9.214.
Yeah, 9.4.
All right. Where did I?
Sometimes it's like things like this are almost like understimulating, so you don't try.
You don't have to make excuses for me. I make mistakes. Yeah, but because this would be, can anybody identify where I went wrong in my addition?
It was you on the.
8 and 8?
second column, You added wrong in the 786 column.
Yeah. This one is 21. Ah, yeah. Oh, yes. 16 plus 6, not 8 plus 6, 18 plus 6. Got it. Thank you. Right, so for subtraction though, it's the same thing. Right, so 5, 6, and then do the math correctly. This is a 3, 0. But now again, so this has just 1 decimal place. This has 3 decimal places. And so we will drop these. Well, actually, this one illustrates a very important point as well. So when we drop these decimal places, we are still going to, just like the other ones, we round based on that first digit that we're dropping. So this is going to round up our 9 to a 1. You have a question?
Calculator, it got it completely different. Yeah, 0.835.
Dang.
The rule you're gonna explain, I still want to know it.
Yeah, no. So forget that. If in this situation, doesn't matter what this is, in this situation, if you got this answer. So we round this up to 1.0.
Okay, so we need to keep that 0.
You keep that 0, you keep that decimal place. So this is where we're talking about, you're talking about that 0.7, when you have those zeros after it, when you not. If you get a calculation like this, where it's going to bump a decimal place or something, or bump you up because you added or subtracted or whatever. So this does have 2 sig figs, but because it's a subtraction and the first one had 1 decimal place, we just keep the 1 decimal place. Right, so we can end up with a different number of significant figures than our initial quantities. So in this case, where we subtract these 2 numbers, I'm just going to use a calculator. 28.02 minus 27.99 is 0.03. So when we're doing multiplication and division, you're always going to have the same number of sig figs as one of your initial quantities, right? The one with the smallest. Here, we went from having 4 sig figs in each of these to just 1. But that's okay. That reflects our precision. Because if you're measuring 2 things, like the difference in like height of 2 things, then your precision is based on how your ruler, which in this case would be the, let's say, 0.01 centimeter. So you wouldn't go and subtract them and somehow your precision gets to smaller numbers than that, because that's not what you measured. So this would be your final answer with just 1 sig fig. All right, so more calculations. And again, right, for these, it doesn't matter how many sig figs, just the number of decimal places. And just like with multiplication and division, you're still carrying through everything until you get to your final answer. Plus 870. Oh, okay. 5.8 something. I thought that there was a. That's enough because, yeah, we have 1 decimal place. So if it was 7.58, my calculator lost it. Right, we remove that. We're going to drop everything past that first decimal place. but we'll round that up to 7.6 because the next digit is an 8. So again, for this next one, 6. So it's our smallest number of decimal places. 2. 131.11. So even though we had one of these that just has 2 sig figs, we do end up with 5 sig figs after that calculation. Any questions, addition, subtraction? So you can have combinations, right? So you can have a whole string of calculations where you're going to do sum addition. After that, you're going to do multiplication or division and vice versa and all intermixed. But the way you do these is you just do them one step at a time. The key difference here is that you have to keep track of in your intermediate steps without rounding how many significant figures you have. So you'll do, in our examples, especially here, parentheses first, but this will also be right, PEMDAS, the order of operations, parentheses, exponents, multiplication, division. So one step at a time, each one considering how many sig figs you're carrying along. Show you how I do that. And then for your final answer, that's when you round. Again, no rounding before that final answer. So if we do this with the parentheses first, 782.3 minus 451.88, we'll get 330.42. This is our intermediate answer. We did subtraction, so we're going to keep the smallest number of decimal places. So we would end up with these as our significant figures.
Okay, so always do the parentheses first and then the significant digit.
Because then in our next step, right, we're going to do this. And now we need to know how many sig figs we're keeping, right? So this is not, I should really rework this so that it's got more in that first number, but actually, yeah, let's just retcon this a little bit. Let's say this 3.89762. So now this first one has 6 significant figures. Our second number, if you weren't keeping track, you might say has 5 significant figures, but in reality, we're only keeping 4 of those because we would have dropped this 2 if it was our final answer. So here now, in our next step, we're only going to keep 4 sig figs. So I'll just use this number that's in here, right? 330.42, not rounding. And we're going to multiply by 3.89762. So our final answer, no. I know there's a way to get the, wait. Man, all right. 330, 42. Come on, technology. 3.89762. Good. Don't go away. Stay right there. All right. So 1,287.8516004. All right. Let's write all that out. So because after this, we only kept 4 sig figs, and this number, we round now our final answer here to 4 sig figs. So it'll be 1, 2, 3, 4, working left to right. It'll be 1,288. Yeah.
Okay, so I blinked and I don't know where you got the 62 from the end of the first. Where did that come from?
The 4.
You just said it.
Oh, the 7. Yeah, the 6.2. Yes. I added that in there to make the point that the number of sig figs that you carry through matters. Yes, yes, yes.
I tried to do a calculation, I looked at the decimal, and I was like, where did that come from?
Yeah.
Thank you.
You know, what, it's okay, I'll talk to you after class because
Okay.
I don't know what the heck just happened up there. And I was watching.
Okay. Yeah, I just multiplied these two.
I'm wondering because I don't know how you chose to have 4 significant figures in the answer to the subtraction problem because I thought subtraction was supposed to be kind of decimal.
Oh, so yeah, right. So if this had been our final answer, if this had been our final answer, right? Because this has 1 decimal place and this one has 2, we would only keep 1 decimal place. So if this had been a final answer, we would have dropped this 2.
But we don't because it's not.
We don't drop it because we're not rounding, but that means that that 2 is not significant.
So that means that when we're counting the significant figures to see what we're going to round to at the end, we don't count that last one. That would
Yes, because otherwise this would have been 5 and our final answer would have been 5. But we would have dropped it. You need to keep it for the calculation so you don't have rounding errors where you start dropping numbers in every calculation step. Yeah.
What if that be 1,275?
So that would be, how many sig figs would that be? 5? 6? 6 sig? Yeah, A5 would be 6. No, so because this one has 6 sig figs, right? This one only has 4 sig figs. That's why I underlined these. That's how I keep track of them. So we did this. Was that? Yes. Multiplication, division, go to the lowest one. This is one of those things that hopefully sinks in. You let it brew a little bit. Keep revisiting it. Continue to ask me questions, please. But yeah, there's just, especially the front end of this class is a massive info dump. And so it will feel overwhelming. Okay, so for this next one though, so we're doing a division here. It's in parentheses first. You get 4.58 divided by 1.239. And that gives us a whole long number. Write out that much of it. But this is where the answer key on your calculator is very handy. So write this down, but we had 3 sig figs here, 4 sig figs here, 3 sig figs, 4 sig figs. So our final, or not our final answer, our intermediate answer is only going to retain these 3 sig figs. You don't round yet. You'll carry the whole number over into your next step, where we're going to now subtract 0.578. So if we do this, right, too many again. And this is why, again, keeping track of which digits are significant is important, because this has 3 decimal places, right? We're doing subtraction, so it's decimal places. In our first number here, way more than that in terms of decimal places, but how many of those decimal places are significant? Just 2. Just 2. This is not a decimal place. Yeah. It's before the decimal place because we're subtracting, right? 3 sig figs, 2 of those are decimal places. So our final answer will be 3.12.